The biggest rule in testing coolers is to never trust anything. Don't trust the numbers, don't trust the software, don't trust the firmware, and definitely don't trust the test bench if it uses a real computer. Every step of the way is a trap lying in wait to sabotage data accuracy. And most people don't even know a fraction of the flaws in their own data. We've spent the last 3 years refining our liquid cooler bench and the last 6 months refining our new testing that will feature air coolers and liquid coolers alike on an AMD platform. With millions of cells of data, we now know enough to have identified nearly every hidden pitfall in testing and finally feel confident in providing a full picture for accurate CPU cooler performance. The downside is that we'll never trust anyone else's numbers again. But the upside is that we can finally start really collecting data. This dissertation will be on the most common and most obscure landmines for testing, laying a plan for our CPU cooler reviews and helping establish a baseline for quality and data accuracy. We promised a CPU air cooler roundup at the end of 2016 or 17, and it took a while for us to finally be comfortable with the numbers we were producing. Before that, this video is brought to you by us and our Patreon page. Aside from the GN store, one of the best ways to support our high expenditure on testing quality and equipment is to join our Patreon page. We've been posting weekly behind-the-scenes videos lately to update our backers on developments at GN. You can gain access to our Patreon Discord, videos featuring other team members, and Patrons Ask GN videos at patreon.com/gamersnexus. The funding has been going straight into maintaining our testing quality. Learn more at the link in the description below. That's really the problem with all of this too, is the more you know about what you're testing, the less you want to know about what you're testing, because as you learn more going through this process, it just instills more of a lack of confidence in any of the data produced, because every step of the way, you get it fully tuned, fully manually controlled, and then the software just decides to randomly run 15 watts less power consumption than last time. Stuff like that, where it really tweaks the data, but you might not ever notice it as a tester, as a technician, until you really crawl through all of the data, not just the thermal numbers, but literally everything you can possibly log. So using things like current clamps to monitor the power going into the EPS 12-volt cables is a necessity now. Using things like this, we engineered this working with a company to manufacture it. This is a dummy heater. It's a thermal test vehicle. We're not ready to publish data only using this yet, but we're using it. We've tested it on one cooler so far, but we're using it internally to validate some of the cooler performance, so we can look at how does the cooler do on this thermal test vehicle where we don't have a motherboard with a whole bunch of parameters involved, and how does it do on the motherboard. And if the data lines up and it's pretty much a linear scaling between A versus B, then we know that the data is accurate, because this can't possibly screw us over like a real computer could. And that's ultimately the big question mark in all of this, is the computer is the variable, everything in there. Motherboard has a lot of different voltages, all of which need to be controlled. The fans need to be plugged into specific headers every single time, because some of them have a different RPM than others. And we will be using this video as, and I'll talk more about this dummy heater later in a separate video in the future, but we'll be using this data and this video as a reference for years. We're going to be linking this one in our CPU cooler reviews going forward, especially for air coolers, which we're finally getting around to doing that roundup. It will establish testing practices and ensure data accuracy on our content. So if you ever have questions about how we're testing stuff, come check this one. Most data out there regarding CPU coolers is flawed in some way or another, but it's just a matter of to what degree and how can you minimize the flaws to the extent possible while still remaining real world. Because as much as we really like these setups with dummy heaters, we do still need real world testing. Even though we've got the Ryzen IHS on there, we have 3 separate heating locations to represent the chiplets, and then we can toggle them individually. All that cool stuff, people will still want to see real world data, and that's the most difficult part to control. So you often see users posting things like, my Wraith Spire is running at 70 degrees Celsius, as if it means something. But it doesn't. And also they probably tested it incorrectly or without any testing at all. So temperature is not a 3D Mark score. It's not just a number that happens and like that's the score of your cooler. It is fully dependent on the power consumed by the CPU. It's dependent on the case you're using, all of that stuff. So what we need to do today is really properly walk through the very basics of how to test a CPU cooler, and then the more advanced stuff of what are all of the things that try to sabotage you along the way. And there's a whole hell of a lot of them. We've thrown out tons of data at this point as we individually step through and figure out more issues with software, with hardware that you wouldn't think would be a problem. So in this content, we're going to show you about 6 months worth of rigorous testing adventures that we've embarked on, including several months worth of discovering flaws in testing, common and uncommon errors, and bad data that invalidate most reviews without the reviewer ever even knowing. We could have started publishing data months ago, or years ago really. And for the most part, it'd be fine, and that it'd be, well, pretty accurate. But at the end of the day, a lot of the small things we found here, it'll skew the data by 1, 2 degrees, maybe 3 degrees. And now when you're talking about a world where it's so refined because it's just physics and there's only so much you can really do, a cooler that's 2 degrees better than another cooler, if your error is that, then you're really not providing that great of a service, which is why we've taken so long to finally do this. So these concepts will range from extremely basic to advanced. We wanted to skip the basics, but we realized that there's so much bad information out there in the community where users, we see what you post online, we see your forum comments and tweets, and a lot of people they'll ask us about their temperature performance, but not really understand that it's not quite so easy. So we want to go over the basics too. You can find all this in written form on the website, of course, linked below, but the video is going to have some extra stuff in it. So with millions of cells of data for CPU coolers and building on top of 3 years of previous testing for closed loop liquid coolers, it's time to go through some of the pitfalls. Within a couple days of this going up, we'll be publishing a mini roundup of air coolers on our new platform. So this will contain all of the methodology, and then that'll allow the future videos to be a bit shorter and we can reference this one. And expect a lot of cooler content from us in the next couple of weeks. Sorry if that's not what you want to see, but we're just going to publish a lot of them kind of back to back, or at least spaced one day out, and then that'll let us get through a bunch of coolers quickly. So in terms of what are we doing, the short version of it is that we fully automated everything at this point. We started this 3 years ago, but we refined it really hard over the last 6 months. It took us a while to really look at it and go, okay, well, we don't really like this. This is kind of weird with Rise and stuff like that. So we've now got automated data monitoring. We have newly added data entry automation as well to eliminate human error on data entry. We have spreadsheets and software that will throw red flags or other conditional alerts for things that look wrong. For example, if you're testing a single cooler against itself, same RPM, same everything, and all you change is the thermal paste, or all you do is remount it, and the temperature range from test A to test B is greater than X, whatever we define, maybe 2 degrees is reasonable, then it'll throw red flags and alert us so that we can look at it and go, okay, well, maybe this seems not realistic and something's actually wrong with the testing. So we've got a lot of stuff like that in the software. We collect hundreds of thousands of data points per cooler, and then we have 45 final numbers that we're evaluating for each cooler tested. It takes forever. It's a human manual process, unfortunately, but have to crawl through all 45 of those numbers. They are averages of averages, and then we look at that for data accuracy and validation. At the end, we work with 5 sets of average numbers. So these numbers are the ones that average thousands of rows of steady state data at this point. So we're sort of narrowing down the data set each time to produce something that is consumable by viewers. And this produces 4 primary charts that we'll be publishing. The current 2 that we're focusing on are, and I'll talk about the frequencies and the voltages in our roundup, our first roundup. You'll also see it on the charts. But we have an overclocked set of numbers, and then we have a stock set of numbers. And what we're worrying about for stock is frequency, not temperature. And what we're worrying about for overclocked is temperature. And I'll talk about why later in this video. So basics, really basic stuff, and also some big errors. For doing this properly, the same CPU has to be used every time, the exact same CPU. Not the same SKU, but literally the same CPU. Because modern CPUs are like GPUs, and each one's a bit different in how it behaves. So that matters a lot. The package is sealed differently. The thickness of the silicone adhesive is different. Even if it's got solder, there's still a layer there for securing everything to get together, and that's different each time. Also have to use the same exact motherboard, have to use identical RAM, obviously, power supply, everything else. We've tied up a whole stack of components that will only ever be used for CPU cooler testing. They are checked out specifically for that bench, won't be used for anything else. And one of the most common errors by people is to sort of spot check some login program for temperature. Typically, this is done by running a test for an arbitrary amount of time, and it's an arbitrary software test. People don't particularly pick any specific thing. They just run their favorite game they've been playing lately, and then look at hardware info, and then they look at the max column, and they look at all the CPU cores if it's Intel, or they look at T-die or whatever, CCD if it's AMD, and pick a number, and then that's what they say their temperature is. So it's not quite that simple. The most common error is spot checking a login program for temperature by looking at the column for max. But in reality, if you look at the maximum column in hardware info, you're doing it wrong, especially with Intel, because those numbers can spike really hard in a way that's not representative of cooler performance. You'll end up with an Intel spike to something like 90 degrees, but then if you properly average it in a spreadsheet, you go through all 1,000 cells of test data at steady state, and you average it, you'll end up at maybe 80. Or you end up with a core-to-core delta sometimes of 30 degrees. And okay, that's fine, but it needs to be accounted for in testing and in the review if you're a reviewer. But if you're a user, you still need to account for it, because if you're not accounting for that core-to-core delta and you just publish, well, my temperature is 90, it's very possible that on a 9980XE, for example, you could have a temperature of 60 average all-core sans one core doing 90. So what's really the temperature? What's really the cooler's capabilities at that point? That's what you're looking at. Also, we probably should talk about what's actually being evaluated here before getting into some of the other mistakes. So to answer how one should properly test coolers, we need to define what it is that's being tested. When we compare the thermal capabilities of one cooler to the next, what we really need to know is what we're looking at there. So ultimately, it's the ability of the cooler to dissipate a known fixed amount of power that the CPU consumes and is outputting as heat. So you won't have any accuracy or like-for-like comparisons if you don't control the power that the CPU is consuming actively for the test. Variables in BIOS and software will invalidate tests. Some software consumes more power than others, and lack of controls means that the technician might never know that there was even a problem, because they thought they had BIOS set the same, they applied thermal paste the same, and they changed the coolers and ran the same program, so everything should be the same in the mind of the technician, but it's really not like that. So power is the single most important aspect for cooler testing, because power is what you're testing. It's just measured as something else. It's measured in this benchmarking as T-die with AMD, or as average all-core with Intel, or whatever it may be. And that's the only thing that really ultimately has to be the same test to test, is how much power is going into the chip and then coming out of it as heat. And then after you account for that, what temperature now is T-die. So if it's 100 watts going into this dummy heater every single test, and we change coolers, then it should be pretty simple. The temperature of the thermal sensor on the Ryzen IHS synthesis should be maybe 70 degrees for the best cooler and maybe 80 degrees for one of the worst coolers. And it should be that simple. Big errors that are often committed other than spot checking the numbers, well, actually in addition to spot checking it, if you have to run a test sufficiently long to achieve steady state. It's not good enough to run Blender's BMW test for 3 minutes. That doesn't demonstrate the performance under real-world conditions. And also, one cooler versus another will perform differently for just 3 minutes. You might have a cooler like a large liquid cooler that's got this extra tank of water that really needs to heat up and reach steady state before you can properly evaluate the thermal result of that cooler. You can't just run 100% fan speeds and have it mean anything without a more normalized test for variables. And we're going to get to a whole lot of charts in a minute, because now you're potentially just looking at fan speed as a test. Doesn't tell you anything. If a cooler is 60 dBA versus a cooler that's 40 dBA, well, the one that's 60 is probably going to be better if all other things are equal. But that doesn't really mean anything other than the fact that the user can spin it up and deal with more heat load at the higher noise level. But in terms of actually using it, it doesn't tell you a lot. So that needs to be controlled. We need a noise normalized test, which we've done for years now, but we're adding more of. Likewise, setting some arbitrary number like 50% fan speed means absolutely nothing, because not every fan is going to run the same at 50% speed. Some of them will have tuning for different performance versus impedance, and if you drop too low arbitrarily, it might actually really invalidate the results and make it unfair. Testing in a case only shows you how the coolers will do in that case, and we have case reviews for that. You've seen how different every case is. So not a good solution to test in a case. You're just creating a case test bench at that point. And you can't trust the computer to do what you think will be consistent. You can't trust the software to do what you think will be consistent. Can't trust what you think is controlled. And ambient temperature is, it must be properly monitored every second of the test. And you also have to know things like, well, if you just looking at the thermostat in your room at the start of a test isn't good enough. Thermostat sensor might be in a different place. The one in our office, for example, that thermostat sensor is not particularly accurate, but it doesn't matter because we have separate thermocouple readers that we read the sense ambient temperature near the test bench rather than just vaguely somewhere in the office, wherever the sensor may be. So a thermostat's not good enough for that. A voltage it must be properly controlled. A common mistake is that people don't control LLC level, don't control the voltage. So you have to control every single voltage in BIOS. vCore is not good enough. You also need SoC or anything else, memory, anything related to voltage that eventually passes through the CPU. You should validate this with a DMM at the back of maybe an MLCC on the back of the motherboard to ensure that you know it's not fluctuating once you've configured it. After you've validated it once, you can probably leave it alone and just match the numbers in software. Paste application has to be consistent. Paste aging and shelf life and batch-to-batch consistency, really important. So to do this properly, you need to use the same paste every time, but we can't use the same jar of paste for 5 years. We're going to have to replace it because it ages, it has a shelf life. If you're buying big tubs of thermal paste because it's cheap, but you're only building a computer every couple of years, then it will age. And the drop in performance can be noticeable. So we have a factory supply of paste. We are able to source it directly through some contacts we have in Asia. And we get we're getting paste that is consistent batch to batch. We've tested it over the last 3 years now. Every time we've gotten it, it's about the same performance. You can validate that on this a lot easier than with a real computer. And we have a supply directly rather than just buying some unknown stuff because the batch consistency might be off. So you need to control which fan header is being used because the RPM will change slightly between headers. The location in the room, the positioning of the vents in the room and the floor, the ceiling, wherever they are, that matters too. And the thermocouple placement for ambient matters. It needs to be not in the path of exhaust of anything. So not in the path of exhaust for the CPU cooler, not in the path of exhaust for the power supply, unless you want to also test the intake versus the exhaust temperature of the CPU cooler, which is data we could collect if we wanted to as well. All right, so those are the most common mistakes. We probably should get into some charts now so that people don't get too bored with this and actually demonstrate some of this stuff. We'll start with power because the most common error that no one knows is happening is that the application may vary in power. This I'm not saying as a comment on our community who post their thermal data, as I'm saying it as a comment on our own data, because when we've done testing over the last 6 months, we've found this, actually over the last 3.5 years, we found this to be a problem where we'll have to just throw away data sets because like, okay, well, this time it ran 15 watts lower for who knows what reason. It just, the software decided to do it. And sometimes that happens, but as long as you know what's happening, you can eliminate for data that's bad. Anyway, let's demonstrate that. So this chart of intentionally bad data will illustrate this for you. These are some test passes we threw out because they were invalid from software variants, not even from technician error on this one. Every one of the lines being slowly drawn should be equal to the lines marked in the legend as good data. So orange and 2 of the blue lines. They all line up with each other. The bad data is first illustrated with one of our Deepcool Assassin 3 test passes. The power consumption spiked from an expected mean of 156 watts up to 163 watts. This spike can influence the rankings and would put the Assassin 3 under an unfairly high heat load compared to the others. 7 watts might not sound like a lot, but when everyone is fighting over fractions of a degree of difference between high-end coolers or low-end coolers, every minute deviation from the mean matters. 7 watts is still an increase in power consumption of about 3.8%. So that matters, and the data is stricken from the results. In a scenario where this happens, we'd investigate it, remount the cooler potentially, reboot a few times, check BIOS, run more tests, and then determine if it's technician error or software error and forge ahead. Another example would be the Cooler Master 200mm cooler you see here. In this bad data, we can see that the initial power spike in the soak test didn't go high enough. So it plateaued at 150 watts instead of 156. The floor also comes down lower to 144 instead of 150. And the next spike is latent despite being an automated test. This is an instance where the software didn't behave as usually expected, and although our test benches are disconnected from the internet and stripped of Windows services as a matter of practice, it's possible that something happened anomalously in the background with scheduling. And I'll note too, that's data from our liquid cooler benches that exist now, so it's not the new stuff. But even if you control the voltages, the frequencies, the ambient temperature, mounting pressure, everything else, it's still possible for the test data to be completely wrong. This most typically happens because applications occasionally exhibit spikes in power run to run. There's a bit of variance, and most people just trust that it's going to work the same way each time, but it does not. In order to eliminate this concern, we hook up a current clamp to the EPS 12-volt cables. We monitor that every millisecond to an external device, so it does not go through the computer at all. And then we check the power input and check that versus software logging, and we make sure that it all looks about the same. So this allows us to keep an eye on things. We also have software that alerts us if it looks wrong. So software alone, the software used to benchmark it isn't good enough, and software monitoring isn't good enough. You need really software and hardware to do it all properly. Next one, here's an example of how power consumption should look. This is our new test bench with a refined method and software that GN custom built to improve automation and reliability of testing. We're using Blender with an animation we created internally for this to reliably produce the same results, and then we have our own external software we've built as well. So this doesn't exist publicly, except for Blender obviously does, and it took months of testing for us to fine tune. The first few lines here are from the Deep Cool Assassin 3 with different speeds and some validation passes. The cooler performed strongly, even with reduced fan speed, as a result of its surface area and contact, clearly, and so power is almost perfectly equivalent from one cooler to the next. There are some spikes up and down, as you can see, but the peak-to-peak delta is now only about 3 watts. So we've halved it. And when looking at initial start of the test and the hottest point in the end, we're really not deviating that much even. Our data is averaged at steady state at the end. The bench must be allowed to warm up for a sufficient period of time. We do about 30 minutes, sometimes it depends on what we're testing. And you have to do that before averaging data because there will be some power leakage over time as well as the CPU gets hotter. In this test, power leakage is low since the cooler is among the best performers. That brings up another point though. Separate from the software variants and issues shown previously, we also have to keep an eye on power leakage and lower end coolers that run hotter. We can next plot one of the lower performers. For this one, the Cooler Master Hyper 212 Evo Black on the same chart is behind the Assassin 3 in thermals in a significant way, to the extent that some additional power leakage shows up in testing. This isn't error and is part of life with a lower end cooler. We can control for this on dummy heaters that we've also built, but at some point you do have to look at the real world implications of using silicon that has additional power leakage external from software testing. In this instance, the power leakage is caused from running hotter, and so is considered a valid metric for the test. The increase is about 4 to 5 watts from leakage. The best way to report on this is to inform viewers of the power leakage change while reporting the thermal results as well. We want to make extremely clear that the previous sample data with variance was specifically from software behavior from the liquid cooler bench and the software's inability to behave precisely the same way each time. Whereas this test shows software behaving the same way, but power numbers changing as a result of cooler inefficiency. That's an important distinction and is another item that most cooler reviews won't notice or point out. We're next going to show you an example of a test bench that was controlled the same way as every other test, but anomalously produced bad data for one run. This chart is intentionally zoomed in. With this one, we used the same BIOS profile as all the other tests, and literally nothing changed on the bench or with the software. And remember, it's not connected to the internet, but vCore still behaved in a non-fixed way, so it's not like Windows is just doing something weird. We ultimately resolved this issue by loading defaults and reapplying the BIOS changes, and it completely solved itself. But this is another item that would produce errors in data and must be closely watched. It'd be easy to miss it if you didn't know to look out for it. We didn't know to look out for this, and it happened at one point in the 6 months past, and we realized, okay, we have to now watch out for vCore randomly not doing what we told it to do. So it's not something anyone would really expect. Our internal charting software looks out for this stuff for us, and since this isn't even technician error, it's an important thing to be aware of. In this chart, you'll notice that the voltage should be a fixed 1.237 volts constantly for this particular test. It should be nearly a perfectly flat and predictable line. In reality, rare test instances like these ran an average voltage of 1.240 to even 1.244 volts instead of 1.237. A range of 1.237 to 1.244 on the second bad data set is pretty high. A fixed of 1.244 is the worst, obviously. This impacts the power consumption of the chip, and it will impact the thermal results during testing, potentially invalidating the results, contingent upon the severity of the change. When we're already contending with potential software challenges, compounding that with erratic voltage behavior can create upwards of 15 watts difference run to run, which is a massive change. We can solve all of this with the software we're using and automating things, but you still have to look out for it. So as for the motherboard's decision to randomly change voltage despite a profile being in play, we solve that with internal and automated red flags and careful technician oversight and retesting. Our future dummy heaters will completely eliminate this concern as well, but we still need real-world testing. Next one. So you can't trust auto. That's bad. One of the biggest mistakes that people do is they just run auto without any control on voltage or anything else. We see this in a lot of comments where people inform us of their cooler performance at temperature Y as if that means anything. So first, if you don't control the frequency on a modern CPU like AMD's Zen architecture, then there's no longer a temperature test primarily. You are not testing temperature now, you're testing something else. So you're probably primarily testing frequency at this point of the CPU. Temperature would be the secondary metric, yes, but the primary is frequency. Voltage still has to be controlled so that the power load remains fixed if you want an auto test of the frequency change versus temperature. Otherwise, the entire test is invalid. The frequency doesn't have to be controlled. It's still a valid metric if it's understood and presented properly. For instance, if you want to show the frequency range produced between the best and the worst coolers tested, that could be done without any controls on the frequency, but you would need controls on everything else, like the voltage. So you can't run full auto. Thermals could be useful as a secondary metric, but because they are no longer comparable head-to-head because the frequency is changing pursuant to the thermals, you now need to look at something else, which would be frequency as the primary comparison. Here's an example in this chart of how frequency changes on the 3800X with full auto settings, aside from XMP, 100% fan speed, stuff like that. The rest is automatic. Frequency bounces between 4125 and 4200 megahertz across the cores. Average core frequency is 4165, but it's all over the place. Voltage, not shown here, goes between 128 and 1.32, and in a pattern which is not repeatable from one test to the next. So if you run this again, it won't be the same. Voltage needs to be controlled in the least, and frequency needs to be reported as a result if not controlled. That's useful anyway, since it puts an actual value aside from, well, we think it runs cooler, on the CPU cooling products. Frequency can be extrapolated to performance in a more direct way than simply lowering the temperature. So these are both very useful numbers if they're reported properly. Fan speeds are next. This is another important one. So this is different on every motherboard. There's no formula to it, but some motherboards will either report fan speeds drastically different one header to the next. Maybe they expect 4 pulls, but they're getting 8. If it's like or well, the opposite. If it's meant for pumps, it's expecting 8 and you're getting 4. It might read differently. So what you need to do is keep the same fan headers every time and the same order for the fans. So every time we're using, for example, CPU 1, if it's a single fan cooler, and we're using pump, if it's got a pump, so that we can be consistent. If it has 2 fans, we'll use CPU 1 and then system 4. If it has 3, we'll use CPU 1, system 4, and system 5. We don't mix them. So we're not going to go to system 1 or system 2 if we're testing something with multiple fans. And that's because it can change. So this chart shows the speed differences. For the most part, we're within error with a laser tachometer. We have an external measurement here because you can't trust BIOS either. So it's about 2000 to 2006 RPM. The CPU fan header runs reliably at 2030 RPM, despite reporting about the same as the others in software. Inversely, System 5 reports significantly higher at 2070 in BIOS, but reads about the same as the others with a physical tachometer, which we trust a whole lot more. Suffice to say, it's best to use the exact same headers, the same order each time, and probably take an external measurement too. One of the larger variables is mounting pressure. Ideally, this would be controllable with a simple torque driver, but it's really not that straightforward. Each of the coolers has a slightly different torque spec with these desktop platforms. Intel HEDT platforms are typically more confined or conformed to one spec, but not always still. In this situation where backplates change, standoffs might or might not be present. Hardware changes from unit to unit. We can't always rely on a torque driver. There's a spec set by AMD, set by Intel, but that doesn't mean the manufacturers follow it. They have a wide berth to follow based on what kind of cooler it is. So you can't just use a torque driver, unfortunately, because a torque number is not always provided by the manufacturers of those coolers. Otherwise, we would just do that. But if you ask cooler manufacturers, like ask our contacts, what's your torque spec for this cooler? Most of them won't know the answer, and it'll take weeks to even get one. Ultimately, what we do is we've determined the best approach is to use torque drivers where specifications are present, which is not common, and to otherwise rely on reason and experience, and then perform multiple mounts and remounts for validation. That's the most important part, is not just simply throwing the cooler on a bench, running it, and saying, wow, that was an easy cooler review. You have to do it multiple times. And full remount. Every piece of hardware has to be removed, put back on the table and put back on the platform to do it properly. So mounting pressure has some of the highest potential to influence performance. It's also the most difficult to screw up if you know what you're doing, so that's good. It's easy to adjust for by doing full remounts, cooler to cooler. If any difference is greater than plus or minus 1 degree Celsius, during this process, we know something's wrong and we start isolating possible flaws in our testing versus flaws in the cooler. This is rare, but it does happen, and the only way to know about it is to actually remount and repaste the cooler. Relying on a single mount and paste job means you'd never really know if your pressure or paste just happened to be wrong that time. Here's a chart with some example data of where the mount was a problem. In this scenario, the first test pass with the stock cooler paste was invalid. First of all, it's basically impossible for paste to be this different cooler to cooler, all else controlled. Thermal Take, secondly, uses Asetex paste anyway, and so do we. So the only actual difference is that the pre-application is slightly less coverage on this particular platform than our manual application. We further determined this data was bad by remounting the cooler and identifying that the mounting hardware might have had a seating issue on the first time, thus creating erroneous data that did not represent performance. Our software and spreadsheets flag these deltas as large and within a single cooler, and we receive a notification to go investigate why such a large gap could exist on one product with the fans at a fixed speed. 10 degrees is obviously not a real result here. So cooler testing properly, there's not really a secret to just doing it right every time. It's all about being equipped with the tools and the knowledge to identify test flaws versus product flaws, because both will happen. That's what we've specialized in for over a decade now in terms of working with products, identifying our mistake versus their mistake to narrow down what's publishable as accurate. And rather than just proclaim that the stock paste is garbage in the instance of the last chart, we investigated more to ensure it wasn't our fault. Now, separately, we have the same silk screens that a lot of these factories use. We've been to a lot of the factories. So we ask for this stuff, and a lot of the time they'll give it to us, especially if you ask the right person who's not in PR. And you maybe sneak off to the side for a second and ask. So we could get the silk screens, and these are the ones that the factories use to pre-apply paste. We don't have all of them, but we also have their stock paste. So we have Shinetsu, we have Dow Corning, the exact SKUs that a lot of the factories use. We have the Asetex paste, and we can effectively retest a pre-application by using the same process as the factories. Take the silk screen, take the paste we know they use, and apply it. And the only way to get this information is to basically talk with PMs and people who are doing the engineering on the product or the manufacturing of the product and bypass PR, because they won't tell you anything. So that's the way to do it properly anyway. And that allows us to get some accuracy there. So we picked up the tools and paste for this job doing some factory work, but that should recap most of it. There's a lot more I can talk about. I see that my timer's at about 40 minutes record time, so we're gonna cut this down a bit, and I'm gonna stop here. But it gives you the basics as far as the test platform. That will be published in the article linked to the description below, and along with the voltages, all the settings we use, all that stuff. I hope this gives you an idea for why you can't trust cooler testing just kind of out of the box. I don't mean that in really any other way than when we get comments all the time or see comments on Twitter or forums or whatever, as people saying, why is your Hyper 212 running at 60 degrees, mine runs at 70? That's not how it works. So that's what we're trying to dispel here. And that's all fine and good if you just want real world numbers for how is your unit doing, but what we care about is objectively how does the cooler perform versus another cooler, not how does the cooler perform in this specific case with this specific setting. So more about this later, but this investing in this stuff has cost us over $10,000 now. We have a couple of them, and we're able to use it at this point to validate specific coolers, but we can't fit all of them on it yet. So I'm working on engineering a solution for that, and we'll talk more about this probably in weeks to months. But for now, we have the real world platform up and going, and I'm happy with it. Finally, it took me years to really get here and 6 months of actual work behind the scenes to do it. So thanks for watching. Subscribe for more. Go to store.gamersnexus.net to help us out directly, or patreon.com/gamersnexus. Seriously, this type of content doesn't get a ton of views normally because it's really long and not particularly exciting about like new Ryzen CPUs. So do help us out on Patreon or the store if you want a one-off purchase and you want to get something in return. It's a big reason we can afford to do this stuff, and we can afford to go dump a ton of money on stuff like this to validate our results. Because at least today I'm not making money on this, but I will eventually, obviously. But if you go to Patreon or the store, that'd help greatly. Thank you for watching. We'll see you all next time.